All right, good evening, everyone, and welcome to this webinar on safety, testing, and adoption of connected autonomous vehicles presented by MCAV. My name is Lakshya Singhani, and I'll be your host for today. Before we begin, I would like to do a quick acknowledgement of country. In spirit of reconciliation, Monash Connected Autonomous Vehicle acknowledges the traditional custodians of country throughout Australia and their connections to land, sea, and community. We pay our respects to the elders past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders of people here today. Also, before we begin and meet our presenters, I would like to give a brief on everyone about how this presentation and the webinar would run. This event would be recorded, and as participants, you all are currently muted with videos turned off. A recorded version of this would be available online, and we would send a link out to our YouTube channel where it will be posted. Please feel free to add any questions you may have at any point in time within the webinar in the Q&A box, which is located at the Zoom control panel at the bottom of your screens. All the questions would be answered in a Q&A session at the end of our presentations. If you're experiencing any technical difficulties, please let us know by emailing us at monashcav@gmail.com so we can fix your issues as soon as possible. So today we have three presenters. Our first one would be Rowan Larkham, the current CEO of MCAV. We then have Mr. James Soo from the Department of Transport. And to round it all off, we have a presentation from Mr. Dotun Ibukun from StreetDrone. After our three presenters, we would move on to a question and answer session where all the questions you have asked with the Q&A function would be answered. So without any further ado, I'm going to turn it over to Mr. Rowan Larkham. He's the current Chief Executive Officer of MCAV. Rowan is a mechanical engineering and science student and has previously been the hardware team lead. So the stage is yours, Rowan, go for it.
Hello, everyone. Thank you for that, Laksh. Firstly, I'd just like to contextualize our team and give you a rundown of what's behind the curtain. Our team was formed at the end of 2018 with the aim of giving Monash students passionate about the future of transport and autonomous technology a research platform. We initially began with just a single vehicle, our Subaru Forester, which was retrofitted by our team to give it autonomous capabilities. Since then, we've acquired a second vehicle, the StreetDrone, which we use as our software development platform. Our team typically works towards an end-of-year demonstration with the aim of expanding our vehicle's capabilities in a connected environment. We're currently organised into 5 sections, and I'll just give you a quick rundown of each of those now. So first of all, we've got our connectivity section. Connectivity primarily works on the software and information sharing aspects of our team. They currently are working on vehicle-to-vehicle and vehicle-to-infrastructure capabilities using onboard cotter units or OBUs and roadside units or RSUs that use DSRC communication. Our connectivity team is also working on our intersection control algorithm, and this is quite crucial to our end-of-year goals, which are built around the intersection control. Interactions focuses on looking at the bigger picture in terms of how vehicle to everything promotes the efficiency and safety of vehicles with a focus on intersections. They primarily use Sumo and Kala to perform simulations for their research, and they are currently looking into the robustness of V2I intersection control by testing the effects of lane closures on traffic flows. Interactions has also been managing a virtual reality project, which is really focused around user experience in autonomous vehicles, and so kind of the people's perception of safety while being in an autonomous vehicle. Our hardware section works on the actuator development and hardware design, as well as our facility management. The sub-team has been hard at work this year developing a chassis for the mini drone project, as well as updated actuation systems for the steering wheel and brake. A dynamic obstacle has also been in development, with prototypes having been produced in semester 1. The software team has primarily focused on level 2 and level 3 autonomy this year. So in layman's terms, basically working on driver assistance features such as lane keeping, adaptive cruise control, and driver monitoring. Software has also been partnering up with hardware on our flagship project for this year, the mini drone, which will be discussed later on. And finally, we have our business section who look after all of our social medias, merchandise, as well as any large scale events such as this webinar. Now we'll jump into the safety aspects of our work and how this year we have really focused on this aspect of autonomous vehicles in order to really accelerate our progress. Before we test any of our software in real life, to ensure a high level of safety, our team performs significant amounts of simulation work. We primarily use Kala, an open source simulator platform. and along with our main software framework, ROS, our development process really allows a lot of flexibility in adapting everything from simulation so that it can be used in real life when the time comes. The StreetDrone is our primary development vehicle. We use this to really test anything in real life. It uses a drive-by-wire system and provides an easily accessible CAN interface so we can directly control its actuation system through software. An extra layer of added safety is that the driver can take control of this vehicle at any stage during testing through like manual input. And obviously this adds an extra fail safe. So if the car starts doing something that we don't want it to, we can stop it from doing that immediately. We have a video for you that shows off our lane keeping simulations in Kala. Once lockdown ends, we plan to test with the StreetDrone, which will allow us to understand really how our Kala simulations can be translated into real life and how well Kala can be trusted. I'll just let the video play for a little bit. Taking a look under the hood, our lane keeping system can be broken down into three main aspects. So we've got our machine learning, which is really all about predicting lanes within an image. Image processing, which is used to identify how far from the center of the lane our vehicle is. And then finally, the controller, which is used to control the steering output, which can be seen on the screen at the moment. Cool. The hardware team has also been taking a safety-first approach at developing this year as well. So firstly, our actuators on the Subaru are currently being updated. So the prototypes for these were originally installed in late 2019 as a proof of concept. And while they worked very well, they required updating for long-term use for our team. So this year, our team has been working on two actuating projects, the brake actuation, as well as the steering actuation. This focus has really been all about safety. So the braking actuator being developed this year, as shown in the video on this slide, it's far more low profile than the original prototype. So this makes it easier for the driver to sit comfortably and press the brake pedal manually in order to stop the vehicle. The steering actuation is also being designed with safety in mind. The new design focuses on being non-invasive to the vehicle and instead will be built around the wheel so the vehicle structure itself is not compromised. The motor responsible for providing the drive for the actuator is also spring-loaded, so it can be disengaged by the driver by simply pulling a lever. This added safety feature ensures that the driver is always able to quickly and efficiently take control of the car if they wish to do so. So if the vehicle starts doing something that you don't want it to, simply pull the lever and you have control of the car. Now we shift gear into how our team goes about testing its work. So our team has been working throughout this year on a project that we've dubbed the mini drone. Was named by our former software lead, Patrick Cleve. The mini drone was conceptualized as a way to introduce our new members to the fundamentals of our work in a low risk environment. So an inherent difficulty of working with an autonomous vehicle is our often inability to easily test frequently. This brings with it the challenge of teaching new members about our existing systems as well as any developments we're making. So with this mini drone, we're able to test our software quickly and easily, and it'll be less confronting for any new members than working with a fully sized vehicle. The development of the project began by focusing on what we dubbed the box. The box is basically the brain of the mini drone. It's the orange box in the image on the right. This was produced earlier in the year and can be used independently of the chassis for road data collection or benchtop testing such as object detection. The prototype of the mini drone was developed with a second box mounted to a stripped down RC car chassis, as you can see in the image as well. The prototype uses a Jetson Nano as its main computer and gathers information from an inertial measurement unit or IMU alongside cameras and a GPS. This was modeled off of the capabilities and information that can be gathered by the StreetDrone. This allows the team members or the new team members as well as existing members the knowledge to be easily transferred to the StreetDrone project when they're working on that as well. The box gives us added flexibility to mount various cameras and LiDAR configurations as well, which allows us to really future-proof any work that we do. Here's a video of the box and the mini drone prototype in action. On the left, we can see the box sitting on top of the dash on a regular vehicle, collecting sensor information. We can even go further than this, and even in testing, we can test our visual algorithms in real time. And on the right, we have an example of the mini drone being used to detect obstacles and apply an emergency braking system. We were able to develop the features like these on a small scale and upscale them to full-size vehicles like the StreetDrone due to the compatibility of our software. While only really demonstrating two cases here, we feel that this project has a large potential in not only developing our members' understanding of autonomous vehicles, but also in helping to bridge the gap between testing and self-driving space. Our hardware team, sorry, is also working to develop the Mark 1 mini drone. This draws on inspiration in appearance, at least, from the Tesla Cybertruck. This vehicle will take all of our team's learnings from the prototype and combine them into one vehicle. We have purposely made this project open source, and in order to give anyone interested the ability to build their own mini drone, so they too can learn about autonomous vehicles in a safe environment. The Mark 1 will also be built from the ground up by our team, and is currently being prototyped at the moment. And it really displays all of our team's hard work over the last year and a half. The final stage of our testing for our software is the StreetDrone. So this is a converted Renault Twizy with autonomous actuation pre-installed. It's basically the mini drone's very big brother, so to speak. After simulating on color, there's small-scale testing on the mini drone. This vehicle is really the final stage of development for our software section. And it really gives us a way of testing our systems in a real world situation in an appropriately sized car, because obviously we don't actually get to test obviously using a mini drone. This gives us a real step up in a real life scenario. Our team has been approved to use this vehicle on Monash's local roads, and testing will begin once lockdown ends. And finally, we'd just like to talk about adoption and how we are working to get our systems out into the real world. So our end of year demonstration, which at this rate will hopefully happen over the summer break, focuses on bringing all of our work together. So we'll be able to bring both our Subaru and StreetDrone into the same intersection and successfully navigate the area safely and effectively. So a mini drone will also be involved as a third vehicle, as well as our dynamic obstacle project, which will be simulating a person crossing the road, as you can see in the simulation above. We will also be looking forward to this display over the summer, and we'll be giving you all updates in terms of location and time of when this will occur. And just lastly, we'd like to thank Monash University for giving us the opportunity to work in such a rapidly developing and really interesting space, and also for providing us the infrastructure and technical skills to do so. Particularly, we'd like to thank our supervisors, Lee Hai Vu, Pascal Mata, and Home Chung, for their assistance, as well as Scott Wordley, the university team supervisor. I'll be passing back to Laksh, the moderator now. Thank you guys for listening. I appreciate it.
Thanks a ton, Ro. And that was, I think, a very good presentation on the whole brief of what MCAV means and what we've been doing over the past year. So moving on to our next speaker tonight is Mr. James Soo. After several leadership roles with Holden and Ford Motor Company for 20 years, James joined the Department of Transport in 2017 to head up the Vehicle Safety Standards and Policy team. A significant focus of his has been developing the strategies, policies, and regulations to accelerate the uptake of emerging vehicle technologies that contribute towards road safety and future mobility outcomes. He leads the team responsible to deliver the $9 million Connected and Automated Vehicle Trials Grant program with industry partners such as Bosch, Telstra, Lexus Australia, and Omniaware, and the TAC support for Australia's readiness for autonomous vehicles. So I'm going to pass it on to Mr. James. It's all yours.
Thanks, Laksh, and really appreciate the opportunity for Monash to invite me to present today. So hoping that this information is going to be helpful as well, and just giving you an update around the work that we're doing in the Department of Transport. So my name is James Soo, Manager in the Victorian Department of Transport, Safer Vehicles and Future Vehicle Technology team. And today, I guess the presentation will be focusing on 3 significant trials that we have conducted recently. And I'll jump straight into it. Next slide, please. So before I get into the details of the trial, I just want to give a quick update around what we do in Department of Transport. You may know that back in 2019, July 2019, the Public Transport Victoria, as well as Vic Roads, amalgamated into one integrated Department of Transport. So, the key role there is obviously to plan and build roads and also infrastructure. The big build that you see going on right now, that's a big part of the work that's happening in terms of planning and constructions of roads and rail, as well as freights and ports. So my team currently sits within the Policy Precincts and Innovation Division. We're responsible in delivering the road safety projects, which are related to vehicle standards, vehicle safety, and also trialing of new and emerging technologies like CAVs, connected automated vehicles. The chart here essentially just shows you what's currently occurring and what our current challenges are. And this is all obviously pre-COVID. We were seeing about 17 million trips that were occurring on a daily basis in Melbourne. And we expect that to grow to about 30 million trips a day by 2050. So that's a real challenge in terms of ensuring that we can get people from A to B and ensuring that we have the transport network that will get them there with the growing population that we're expecting, which is about 2,000 people arriving in Melbourne every single week, and this is all based on the census data back in 2016. So obviously that's all pre-COVID. With how things are progressing, we were expecting to overtake Sydney as the most popular city in Australia by 2050. And I guess part of our work is to ensure that we are progressive, we are looking ahead and ensuring that we are prepared for new technology to help with our transport challenges. Next slide. So under the previous road safety strategy towards zero, the Victorian government made a commitment to facilitate trials of connected and automated vehicles to help inform its future development and also support the state's readiness for emerging vehicle technology. And back in 2017, the $9 million MCAV trial grants program was launched, and it had a very strong road safety focus in order for us to better understand the potential technologies that could lead to reduced deaths and serious injuries on our roads. And we were really keen to understand what systems and technologies can best help us minimize the risk on our roads and what we need to do to support and facilitate the future planning for infrastructure and as well as the road design and CAV technology requirements. So we went through a very extensive EOI process and expression of interest process where 3 projects were selected, and I'll be going through these in a bit of detail. Next slide. The first one is the Omniaware project, and this is what I call the infrastructure project. It's essentially Omniaware is a consortium of transport expert organizations, which the Department of Transport had partnered with. And the idea of the project is really to develop and adapt perception technologies that are derived from automated vehicles to the roadside use. And again, it's in order for us to predict crashes and near misses using LiDARs that are fitted. So multiple LiDARs and cameras were installed at a particular intersection in Yarraville, where we built a continuous spatial awareness of pedestrians, cyclists, cars, buses, and trucks. And essentially, using the technology from the smartest AV and making the smartest roads and improving safety. So that was really the idea. The key focus is to enable the benefits of AV technology for all road users sooner by exploring their application on the infrastructure. And we were able to apply the cooperative intelligent transport system through the connectivity portal for us to inform other road users of potential hazards. So it's really using the technology to detect the hazard and then be able to communicate that. So the trial commenced back in 2018 and was recently completed in April this year. There was a large amount of data that was collected, over 110 terabytes. I guess, we're in the process of also intending to sharing that to researchers like yourself in developing it further. Next slide. So just to give you an idea, this is really a snapshot of what the LiDARs can pick up. And after quite a bit of off-road testing, this site in Yarraville became operational in November 2019. And the aim here is really to detect the crashes and near misses in real time and then be able to send these warning messages to connected vehicles in the future. You can see here on this slide, the object model output from the system. Essentially on the left here, you have the 4 cameras at the top of the screen, which is more for reference. And the large picture is essentially what the LiDARs can pick up. in terms of detecting the truck. You can see it's quite prominent. It's yeah, just a really, really precise way of picking up the information at the intersection. Next slide. Just to give you a better idea, I'll just run through this video. It's just a bit of background as well in terms of why we selected the intersection, because we know that over a third of lives lost on our roads are occurring at the intersection, and about 44% of serious injuries occur at intersections in Victoria. So in this example, you can see how the raw data from the 4 LiDARs are being merged into this object identification and classification processes. The data is then processed and fused in real time, and it allows it to also record the accurate position, direction, speed, and acceleration of each of these road users at the intersection. Okay, next slide. Excuse me. So yeah, just a real quick summary in terms of what the findings were. We managed to see that there is a lot of potential with LiDARs. We found that it had a very strong spatial accuracy up to within 10 centimeters. And the high fidelity to the point cloud was collected as well through this LiDAR. The hazard identification was also very rapid. It can detect any hazards at less than 0.2 of a second. So you can see that there is a huge potential there for us to do that in the future. And also the LiDARs provided a full 360-degree view, and their performance, unlike cameras, was not degraded by environmental conditions like wind and rain. And we're also able to confirm the communication through CITS warning functions with the Q3 equipment that we used at the trial. So I won't go into detail, but essentially those were essentially some of the key learnings. Next slide. The second trial I'd like to talk about, and this is also something that I'll be presenting at the Australasian Road Safety Conference in a bit more detail. So if you're interested, that's going to be presented next week. I can send you some information there if you're interested after this presentation. The trial is really involving our partners, Telstra and Lexus, in developing a communication protocol using cellular network or CV2X, cellular to everything technology. It allows vehicles to communicate directly between themselves. It also allows the vehicles to communicate with a lot of our infrastructure, such as our speed signs, roadworks, as well as variable speed limits that we currently produce. So the vehicles can ingest a lot of the information and then providing some of the safety warnings to other road users in the effort to help with safety outcomes. The key focus, I guess, it's to contribute to the Victorian knowledge base as to why we're doing this. Our knowledge base around connected vehicles, it's important that we have that. And the potential of the road safety benefits in future scenarios, because there are a number of different use cases that we have tried in this trial that can produce some safety outcomes for us in the future. And also to be able to support our physical and digital infrastructure, both at the urban and rural settings. So not just in the metro area, but also looking broader as well into the regional areas. So there were a number of real-world applications that relates to speed management and intersection crashes, as well as the vehicles in hazardous situations that we trial in this project. Next slide, please. So a little bit about cellular V2X, if you're not familiar with it. I guess this is a schematic of what it looks like in terms of the trial that we've used. CV2X is essentially a form of CITS technology using cellular network to allow vehicles to talk to each other, but also allows the connected vehicles to ingest the information from road authorities, such as our roadworks, speed data, and traffic signal timing. And in this trial, an enhanced version of the Telstra 4G network was used to develop a vehicle connectivity ecosystem. And this is where the Telstra hosted cloud ingested data from the department and other sources and was able to communicate the messages to the vehicles where relevant. So from this diagram, you can see that the vehicles were capable of communicating as well directly with each other through this direct comms protocol, PC5. That's what it's called at the bottom there. And the messages were also able to be communicated over the cellular network between the vehicles too. So it's essentially V to N to V going up to the cloud. Okay. Next slide, please. And it's, so in terms of summary of the use cases, you can see here there were 6 use cases trial, and a lot of these are typically referred to the day 1 CITS use case. They're pretty standard. And the research by Austroads and more recently by ITS Australia has indicated that a lot of these use cases can provide significant road safety benefits to Australia, some up to between 30 to 50% reduction in crashes have been estimated if the technology was widely deployed. I won't go through this in detail, but essentially you can see in the diagram, some of these are essentially providing the warning messages before it can be detected by the human. So that split second is so critical that could potentially minimize that crash event or potentially avoiding it altogether. Next slide. I'll just maybe take you through one example in a bit of detail, which is the electronic emergency brake light use case, which is when the sudden braking of a vehicle ahead is being received by the following vehicles as a warning alert. So the benefit of this technology is that it doesn't require a line of sight. So even if the vehicle ahead, say, is obstructed by a truck or any other vehicles, a warning can still be sent, and this allows the drivers who may be inattentive or may have their vision obscured to receive this warning message and take evasive action as quickly as possible. The warning could be provided in around 0.1 of a second, which is minimal addition to the reaction time of a human, and this could be the difference in helping the driver avoiding the collision altogether. Next slide. The other use case, which I obviously don't have time today to go through in detail, are shown in this picture here. The vehicles, I guess, were equipped with a bunch of hardware and comms and integration with the vehicle controls, as well as an aftermarket screen that you see here that was giving out the visual warnings to the driver. And the vehicle was also fitted with high precision GPS and cameras to record them. So the top left picture is a right turn assist for pedestrian. And this is where the vehicle can detect the pedestrian crossing and potentially alerting the driver as he or she is about to turn right. So, potentially allowing the driver to slow down if necessary. The top right-hand corner is a red light violation warning use case, which uses the interaction with our traffic control signaling. So it actually communicates with our traffic signals to see if it's a green light or red light. And where there is another vehicle that has gone through a red light, it actually triggers the alert to the other vehicle to not approach it, even though he or she has the right of way, you can see in this picture, to stop in this picture. Yeah. And the last one at the bottom is a curve speed warning. Again, this is just warning the driver of an imminent corner ahead to slow down. Next slide. So yeah, just to sum up some of the key lessons learned from the Telstra Lexus trial is that we were able to efficiently deliver the safety critical messages to vehicles. The system latency was considered to be very low, and they can be delivered to drivers in milliseconds. which is, in terms of both the short range communication between vehicles and also for the wider communication facilitated by the Telstra network. The infrastructure related information like traffic light timing and speed zones can also be distributed to the vehicles through this network. And it was clear that the successful communication between vehicles of different types require commonality of rules and standards. So, obviously conducting the trial with 2 Lexus vehicles is kind of a proof of concept, but to realize the true benefits, it will require much larger scale adoption and I guess a harmonized approach as well in terms of standards going forward. Next slide. So the last trial out of the 3 is the Bosch Highway Pilot on Rural Roads trial. So this is what I call a truly automated vehicle trial, where we partnered with Bosch Australia to essentially redevelop the vehicle and rebuild the vehicle, which was originally a Tesla Model S, into a vehicle that has capability of level 3 plus automated driving capability. The trial was undertaken at a regional setting because more again for the road safety reasons, we have an overrepresentation in terms of road crashes and fatalities on country rural roads, where nearly half of all our fatalities in Victoria occur out there, and a lot of them are related to runoff roads, head-on crashes as well. And you can just imagine a lot of high speed limit roads people are traveling at, and can has grave consequences if they're not if vehicles are veering off and not having the technology to prevent them from doing that. So that's the idea behind the Bosch trial, is to develop the technology to see what can we do, what do we need from an infrastructure perspective and maintenance requirements on our network in our infrastructure to help support these vehicles of the future. It is also quite a unique opportunity for us to be partnering with a global partner like Bosch, and also be, they do supply a lot of to a lot of major automotive vehicle manufacturers. So really getting that insight was invaluable. So we managed to cover over 14,000 kilometers during the development, where 2,700 kilometers were conducted in automated driving mode. Next slide. Like I said, the involvement with Bosch was quite unique. We were a little bit fortunate as well. They were based in Australia, in Melbourne, and we've had this long-standing relationship even back in 2015, 2016, when we trial with Bosch at the, I guess, a less sort of a complicated scenario where it was in a low-speed semi-urban environment at Albert Park. So that was part of the ITS World Congress. And since then, the team has developed the system further to enable its operation on higher speed motorway in 2018. And again, more recently in this trial, we had the team essentially overhaul the entire vehicle, rebuilt it with new LiDARs, new sensors, new radars, and be able to rehash it to a point that it became level 3 plus automation. So that's really the journey that we've had with Bosch. And next slide. So in terms of key findings, we've acknowledged that there is a need for strong and continued collaboration between industry and government agencies for us to facilitate automated driving technology in Australia. It's really an effort that's required from both sides. We've seen from the Bosch trial, high definition mapping is a really critical component for us to ensure that there are standards going forward. I think that's a key step in addressing some of the challenges that we've seen. There are currently no standards for high definition maps or readily available of HD maps in Victoria. for Victorian roads. So somebody actually has to go and source that information. And in this case, there was another Tesla vehicle that was used for mapping purposes. And the other vehicle that you saw there before, that was the automated vehicle that was used for automated driving. Yeah, and I guess the other lessons learned were that the regional roads have a relatively scarcity of roadside features, which is important for vehicles to be able to use some of these roadside features to detect and localize their positioning. And that's very, very critical in order to localize itself accurately. And also what we've seen is that the radar landmark-based localization was able to be compensated in situations where inputs of camera-based landmarks and differential sat-nav were degraded or unavailable. So you got to have some redundancy in the system to enable technologies like this to work. Next slide. Yeah, so this slide really just highlights the other work that we've been doing, which is to establish a regulatory framework, which we know it's very critical in signaling to the community as well as the industry that automated vehicles are being trialed in a safe and managed way. So back in 2017, the legislation was passed in Victoria to allow us to trial highly automated vehicles successfully and safely. So the automated driving system permit scheme essentially is now active, and we've had a number of permits now issued. And that obviously applies only if the vehicle is capable of driving up to level 3 and above. So in this case with the Bosch, they were this first recipient of the ADS permit in Australia, and we've obviously also had the Monash Tweezy that you mentioned earlier, that also has been issued with a permit to operate. So yeah, next slide. I think that could be the last. Yeah, so that essentially concludes my presentation. Hopefully that was helpful for you all to take away, and also highlight some of the work that we've been doing in Victoria. And yeah, happy to take questions at the end. But if you have any other questions I may not be able to answer today, just feel free to reach out to me with that email there. And again, I mentioned if you are interested in knowing a bit more about the 3 trials that I mentioned today, my team and myself will be presenting at the Australasian Road Safety Conference next week. So yeah, there is a link there if you're interested in registering. Thank you.
Thank you so much, James. To be honest, I think I have taken 2 really important key points from your talk. Firstly, as a student of robotics, I find it really interesting that whenever I want to learn something new about robotics, I move more towards, let's say, mobile vehicles or like mobile robotics, including drones or cars. But no one really thinks about using the same technologies and sensors like LiDARs and cameras to something, that basically goes under the radar. Like the Omniaware trial that you talked about, that was really interesting to see the same key principles of robotics, like image stitching, clustering, being used for something, that it basically helps a lot more people than just looks fancy. I think the second thing that I really took away was being realistic, because people really talk about using AI and machine learning for every small thing, but safety is so important when it comes to making something like an autonomous vehicle or anything in robotics in general. And I think that kind of flies off the radar as well, just because I think it's a lot more fun to make something that's new, but definitely safety has to be on top. So thank you so much, James. I thought that was a really great presentation. So moving on to the next speaker of the webinar, we have Dotun Ibukun, with several years of experience in the automotive industry, working in companies such as Cummins Incorporated. In July 2020, Dotun became the business development manager at StreetDrone, a company committed to building technology that lowers the cost of autonomy for faster and safer development of autonomous vehicles at scale. Alongside his full-time role there, Dotun is currently completing his Masters of Engineering Business Management at the University of Warwick. So welcome, Dotun, and I'm keen to see what you present to us today.
Perfect. Thank you very much, Lakesh. Hi, everyone. So let's go to the next slide, please. So I just thought I'd introduce StreetDrone, and it's interesting because there's probably more about StreetDrone throughout this webinar than I thought. So I don't have to say too much. Thank you, guys. So StreetDrone is a tech startup based in the UK. We are specifically in Oxford, and we are the first company to actually deploy, well, the first company in Europe to deploy an autonomous vehicle using an open source project. So StreetDrone provides our customers with vehicle platforms and software available to deploy vehicles on public roads or on private roads. StreetDrone has two offerings in terms of our vehicles. However, our real IP is on the drive-by-wire side. So the drive-by-wire consists of your steering by wire, your throttle by wire, and your brake by wire. And what that means for us is, we come from a Formula 1 and Formula E background where we build technologies in general, and it's obviously quite sensible for us to try to help accelerate the development of autonomous technology. So StreetDrone, apart from just software, we also look into cloud integration, and what that does for us is being able to use teleoperation to bridge the gap within autonomy. We were founded in 2017 by Mike Ports and Mark Preston. Mark Preston is a Formula E team principal, and Mike Ports is a digital entrepreneur. So what that means is we have the technology, the technical experience within the team, and we have about 25 engineers working out of Oxford, our HQ, and we have about 27 vehicles, actually 28 now, with our drive-by-wire technologies in them. So speaking about the 28th vehicle, I will show you some pictures of the latest vehicle that we are developing, which is really exciting. Hint, hint, it's a truck. Next slide, please. So StreetDrone, we've developed, we've been doing a lot of development around technologies, and I think James can echo what I'm saying here in terms of the trials. They can be long, and they are very resource intensive. So that's what StreetDrone has been working on over the past few years. I'd say the last 4 or 5 years now. And the first one on the left-hand side you can see is a public road trial. The videos are available on YouTube, but I think everyone has sort of used video bandwidth for today. So I'm just going to allow you guys to take, this slide. Nick can share this slide to you guys at the end of the session, where you'll be able to click on the videos and watch them. But the video on the left is Smart Mobility Living Lab London, which is one of our public road trials that we conducted in London. So on the right-hand side is just one of our commercial videos introducing StreetDrone vehicles, and both these vehicles have our drive-by-wire systems embedded in them. Just to be clear, this is level 2, and I think my colleague Rowan has helped explain what that means in layman terms. And it's very, it's straightforward. It's about the driver assistance for kind of getting us to the step of autonomy. And I'll talk about what we're doing in terms of the future deployments. And below is just one of our customers, which we've sold our vehicles to. And out of the 27 vehicles, as you can imagine, they're spread around the world. We're based in Oxford. We've got some vehicles as close as London, and obviously as far as Monash in Australia, and also Hong Kong as well. So it's pretty interesting how we're able to do this at the same time as trying to use autonomy for good. Next slide, please. So in terms of the StreetDrone technology stack, I just want to say that there's 3 parts. So the vehicle platforms, and like Lakesh actually said after James's presentation, we're not, we've only just started looking at bespoke vehicles. And as you can see behind me I don't know if you guys can see behind me on the camera screen. The background of my webcam is actually the newest StreetDrone vehicle, which is at its concept stage, and it's called the Pixie. So if you'd like to see, find out more information about that, you can visit our website at streetdrone.com to have a look at what we're doing there. So we've only just announced that recently, and that's based on some investment that we received from Wilkinson's Retail. It's a big retail chain who has invested in us. And we're basically going to help them understand how we can deliver autonomy to their customers' doorsteps. So the way we do this is obviously by our tech stack. So understanding the vehicle platform is really important, and making sure that there's no smoke and mirrors when it comes to creating bespoke vehicles. It's all about using the vehicles that are already available. Taking an OEM vehicle, we can retrofit is the term that we use in terms of how we fit our sensors and our safety systems and compute into any vehicle. So the reason why we have just a Twizy and an ENV200 is our customers have asked for a bigger vehicle that can fit human passengers in it. So imagine if you were trialing the shuttle type application, then we can also fit that into the use cases. With the Renault Twizy, it was a simple vehicle. My boss coming from Formula One likes to call these sort of vehicles dumb vehicles, because they don't really have any sort of capability that allows them that makes it difficult for us to retrofit our sensors. But what that also means is it's really easy to understand, and it's really perfect for universities to work on, as Rowan mentioned previously. But what I found really interesting as well is the mini drone, which is, I'm sure I'll catch up with Rowan on that. It sounds really interesting because it's always good to be able to do more things with a smaller vehicle, because the cost of damaging a big street drone vehicle is just, you don't want to do that basically. So if you could work on a smaller vehicle and then bring the things that you're working on into a larger scale, then at least that you've tested it and it's doing exactly what you're expecting. The other thing is our autonomous software. So StreetDrone released Project Aslan about a year ago now, and Project Aslan was one of those sort of collaboration ideas that we came up with, and we wanted to bring universities together. We wanted to bring industry partners together to work on the autonomous industry activities, the difficult to solve problems, but also with a commercial goal that allows us to say, okay, we are going to achieve autonomy together, either if it's low speed or high speed. We just want to do something that has a commercial goal at the end of it. In terms of connected cloud, like I mentioned, all of our vehicles have 4G and Wi-Fi connectivity, and more recently we're working on 5G in our vehicles as part of sort of the trials, which I'll mention later on. StreetDrone has, we've now coupled with teleoperation technologies, and to give you a brief background, teleoperation is essentially using the network, either your network, your phone network, or a 5G type network to teleoperate a vehicle. So to operate a vehicle from outside the vehicle, and you can be miles away depending on the connectivity for sure. But this allows us to be able to maneuver the vehicles when it's a really difficult task that autonomy hasn't reached yet. Next slide, please. So the anatomy of street drone autonomy, what this means is how do we actually deploy a vehicle? And James has probably mentioned some of these things, but I'll just sort of go through it quite quickly because in the interest of time. Once again, the first thing we think about is the public road deployment. What do we need for deploying a street drone vehicle, for example? And what we need there is a safety driver and a trained software engineer. With that being said, a safety driver always needs to be in the loop, and the reason for that is so we can make sure that the safety driver can take over if there's anything abnormal coming out of the system. Typically, it's quite easy as well to take over from the from being in autonomous mode as well. We also have to create a comprehensive safety case as part of that sort of process, and we want to make sure that all the stakeholders are aware of what the safety case would contain, and a cut down version or a shorter version will be available publicly when we deploy these vehicles. So typically we have, let's say, the Oxford Council, for example, if we're deploying in Oxford, or we would have James's team involved in that process to understand what, how deep we're taking the risk management. The system safety is another thing that needs to be taken into consideration, looking at the compliance check, cybersecurity analysis. Cybersecurity is quite interesting because not a lot of organizations are looking at that, but it's really important. But we are one of probably the first companies to make sure that we're investing on cybersecurity, make sure that we're actually spending time to see what the risks are and understanding the security protocols. We also test on test tracks and closed roads to make sure that we can do live testing as well, instead of just visual testing. Simulation verification is really important. As Robin had already mentioned, you guys are using Carla at Monash, which is really good because it gives you close to real world scenarios. And we also use IPG for more commercial solutions. And quickly, operational safety. This is all around the operational design domain. What are the operational guidance, the risk assessments, the stakeholder engagement, who do we have to talk to, local authorities, landowners, CCAV. CCAV is a connected autonomous vehicle government office, which basically looks at what sort of deployments are going on around the areas. And emergency services are also needed to be consulted to speak to them about how do we deploy this safely. I think the bottom line is no one wants to go to prison and no one wants to hit anyone. So the idea is we want to make sure that everyone is aware of what we're doing. And it has to be a really in-depth sort of conversation. And then we define the ODD once we've taken into consideration all of the assessments. And then StreetDrone, what we're really good at is retrofitting those vehicles with the right sensors. So we spec the LiDARs, we spec the radars, we pick the GPS cameras, ultrasound, and we fit them all on the vehicle. Sometimes they look very research and development focused, which means they're not very sexy. They don't look amazing sometimes, but it's all meant to be functionally right. So it works. And obviously when you get to producing a vehicle like the one behind me, then you can make it look very sexy because it's very customer facing. And Enterprise Aslan is the enterprise version of our Project Aslan, which we are launching. And the idea around that is we take some liability around how you deploy the vehicle. And with the StreetDrone vehicles, we want to take liability with our customers when we help them to do all of this stuff. So anything that we do in terms of the operational safety, the system safety, we take liability for. And the XCU retrofits, like I mentioned, we can fit any of those, the drive-by-wire into any vehicles. And there are about 2 sensors minimum per function. And what that means is for your steering, for example, we have 2 sensors, 2 ECUs, one taking a sort of monitor control and the other taking a master control. And then the type approved base vehicles, so any vehicle form factor. So next slide, please. So the recent project that we're doing is this Turberg tractor. So we've taken a Turberg electric tractor or truck. It's a 40-ton HGV vehicle. And we're basically, this is a government-funded project, which is allowing us to prove our technology on a big scale. And you can see that some of the guys that support this project are, big players in the game. So Nissan, for example, Vantech. So Vantech is a huge logistics organization that supports Nissan, and they're owned by Hitachi. So it's really interesting what we do there. And Turberg are helping us with the retrofit of the vehicle. They're providing, the partnership that we have with Turberg allows us to understand a bit more about their vehicle, because yes, we can fit any vehicle, but we also need to have an OEM relationship to help us understand how the vehicle actually operates. And this project is basically, sorry, next slide. I'm just going to talk about that bit in a second. So this project is about a trial route. It's quite a simple trial route, but it's also very complex when you're doing autonomy. Nothing is really simple. And what we're doing is moving parts for Vantech from one part of the Nissan factory to another part. So that's the location, and that's the drop-off point for Nissan. So that's the Vantech building there. Next slide, please. I'm just aware of time, but you guys can absolutely get in touch if you have any questions. So we started this project at the beginning of this year, and we've been, sorry, that's wrong. We started this project about 3 months ago, actually, but we've done a lot, so it feels like it's been the beginning of this year. So we started with a test mule, and that test mule is the Nissan ENV200, which basically replicates everything that we're going to fit on the truck. So the Nissan test mule is basically an easier vehicle for us to be able to retrofit and to understand what does it look like on a Turboc truck, because for a government-funded project, you only get one vehicle in terms of the budget, so you want to make sure that everything is right because it's the first time doing it. And as you can see there, we've been at Nissan conducting some of the works. We've been at Vantech next door, and we're also using IPG simulation there. So, we've done some vehicle in the loop testing simulation that allows us to spoof the vehicle in real life. So it sort of reacts the same way that it would in, it reacts in simulation the same way we're expecting it to react in real life. Next slide, please. Thank you very much, guys. In terms of the truck, we're expecting to deliver that project at the end of March in 2022, and I'm sure Nick will probably get in touch with me about some of the information, and I'm happy to share that with you guys. But yeah, if you have any questions, please get in touch. Thank you.
Thank you, Dotun. One thing I would like to bring up is in the past at MCAV, one of the big problems we've had is having the hardware to test the software that we have. And the thing with building hardware ourselves is sometimes we might have things not in the right place. So even though our software might be on point, stuff doesn't work. So having professionals, make us a StreetDrone that is well built, has everything in the right place with a right manual that we can go through, makes testing very easy, and also saves us money in the long run. Another thing is, I just love how, so recently we had a chat with Dr. Ram Ramamurthy from 5AI in the UK, and he's in close contact with Wave.ai, and you are in close contact with it. So I love how we're making this small family of connected autonomous vehicles.
Absolutely. Wave were actually our first customers back in 2017. So it's really interesting. Absolutely. It's a small world for sure.
Amazing. All right. Sorry about that. So now we would move on to our question and answer session. So I do see that we have a question already posted up, and this is from a supervisor, Lehigh Vu. So this is directed to James. He asks, what are the key lessons or gaps learned from these 3 trials that you stated? Are there any plans for the future trials? And how would you address them?
Yeah, thanks, Hi, for the question. Really good question. We, I guess, continue to work in this space in the department. We, have completed the 3 CAV trials that I've presented today, but there are already a number of other activities happening that we're looking at to progress the work and also the findings that we found. I guess the key learnings, there were a lot because each of the 3 trials produce a number of their own set of learnings and findings. But I think the biggest one is around the need for us to continue to collaborate with the industry, with researchers like yourself. I think that's going to be an important piece. We all have our role to play in the development of CAVs. From a government perspective, we see our role to facilitate and help, having the regulations that are flexible and ensuring that we do not stifle innovation and ensuring that we are not picking a particular technology. So really, yeah, ensuring that we have trial and tested, the different type of technologies and allowing the industry with that test bed to be able to do that properly. I think the aspects around standards, that's probably another area that we, as government and the industry, can also work together on that and defining that, because that could also provide a bit of certainty as to how protocols could be designed in the future. Having those standards in place would potentially help accelerate that. So yeah, hopefully that answers the question.
I think it definitely does. Thanks, James. So we've got a question for Rowan. Regarding the changes on the Subaru actuation, what were the main reasons you moved away from the original prototype designs?
I guess like the main, like, so I'll explain going over both prototypes. So like with the braking actuator, as our supervisor Pascal will be able to testify, obviously having a lever that's effectively in the footwell creates a very uncomfortable ride, and I think that contributes to creating an unsafe environment. Obviously, you want someone to be sitting in a comfortable position in the vehicle. As well as the lever itself was pushing on the brake. So obviously having a like a pseudo foot on the actual brake itself, it makes it difficult to press the brake because there's already a foot there effectively. So the new actuator has basically it's been attached to the drive shaft of the car itself, and it more or less reaches around behind the brake and pulls it in. So it enables like whoever's driving the car to be able to press the brake normal, while also being able to actuate the way that we want as well. And then with the steering wheel actuation, it was all about being able to quickly and effectively disengage it if we needed to. Obviously, like an issue with it would be if we were doing testing and for whatever reason we lost power to the motor, or the system just froze, and then all of a sudden the car's just doing something that you really don't want it to do, and there's no real way of quickly being able to take control of the car. So the main problem was that trying to get control of the vehicle. So this new system being able to mechanically disengage the motor ensures the fact that if someone doesn't like what the car is doing, they can quickly just pull the lever. Motor falls back, so the gears disengage effectively. So there's absolutely no way that power can be transferred from the motor to the actual wheel itself. So that ensures that we were really focusing on safety, because if we had a different system that worked 99.9% of the time, that's not good enough. It needs to be a system that'll work 100 times out of 100. So that's kind of what we were going for with our new design over the prototype. Hope that answers the question.
Yep. Thanks, Rowan. So we have a question from Owen, and I think this should be directed towards Dotun. So what are some difficulties that Streetrun has faced in adapting work done in simulation to real life?
Yes, absolutely. The interesting thing for us is we started off using Gazebo, so a really basic simulation kit, and it doesn't really show you as much information as you need, but it's sort of good for the basics. And then we moved on to IPG for this sort of truck project, and even with our ENV 200, we've been able to do some simulation. But more recently, it's more about the vehicle in the loop testing, where we want to make sure that that we're basically able to replicate the exact scenarios, and actually potentially there's a billion use cases that you could test with simulation. But sometimes each variant of real life activity is not equal to what's actually happening in simulation. So our struggle is actually understanding where do you stop testing, because you've got so many scenarios that have, even more scenarios of those scenarios. And I think that's the biggest challenge for us, really, because we can, and there's no sort of there's no fast rule to say that, we've tested enough. Because there's just, there needs to be a lot of testing before the vehicles are trusted on public roads. So that's the challenge for us, really, being able to have enough data sets, or edge cases rather, to test on simulation.
Yep.
Hope
I have
that answers the question.
Oh, definitely does. With regards to edge cases, we at MCAV have had a few. Luckily, we have a mini drone that saves us from, damaging the precious StreetDrone we have.
Yeah.
I have a question for James from Liam. So what are the estimates for how far away an infrastructure project may be in Victoria for supporting mass use of autonomous vehicles, such as Omniaware?
Yeah, really good question. The Omniaware was a little bit unique because it was more of a proof of concept. We know that the broader, larger scale deployment based on the current technology is probably not feasible from a cost perspective. But yeah, essentially, I think as we go, further down the track, hopefully with the cost coming down with time, there could be a potential use of that, or even exploring other technologies such as better high definition cameras. But yeah, it was more a proof of concept to understand, is there a particular technology that currently exists which is being used in AVs could be applied at an intersection. So yeah, there are no definitive plan at this point in time to be deploying this in a larger scale, just purely because of the cost reasons.
Thanks, James. So we have a question for Dotun from Dylan. He really liked how the team focused on the cybersecurity aspect of StreetDrone. But why do you think cybersecurity is being neglected by other companies?
Okay, I'm not muted. Good. Perhaps I think the reason is there's so much in the puzzle of achieving autonomy that I guess cybersecurity just becomes that thing that's sort of left behind by many organizations. But I think StreetDrone, we've grown some partnerships around cybersecurity and how to make sure that we're sharing our vehicles in the right way, and we're following a process. So yeah, it's just one of those things that even cybersecurity in our day-to-day lives is really important, because there's a lot of risks out there, and we want to mitigate as many risks as possible. So for us, it's just really important. And like I said previously, we want to avoid any sort of issues with regulations, or potentially someone going to prison. So because you're testing live vehicles, you've got to you've got to think ahead of what are the potential issues apart from just the operational design domain. What are the issues around deploying vehicles safely on public roads? And that's where cybersecurity comes as one of our top concerns.
Is there a big cost aspect towards installing cybersecurity within autonomous vehicles? Is that maybe why other companies are a bit focused on, let's get the car running first and then we'll think about it, kind of?
Yeah, there is a cost factor. I think luckily in the UK, I think similar to Australia as well, there are lots of government funded activities, which is, I think the government are quite aware that cybersecurity could become an issue for autonomous vehicle developers. So there's a lot of opportunities for collaboration, which sort of answers that question for us, really. There's a lot of research and development money around for cybersecurity. So it means that there's an importance there, and it means that someone needs to do the work. So StreetDrone are interested in integrating and making sure that we're cyber safe.
Amazing. So we do have one last question from Josh, and I think I'm going to throw this out to anyone who would like to answer. It is a very wide question, but so what do you think is the current progress towards standardizing how connected autonomous vehicles communicate with each other?
I'm happy to have a go
Sure,
at that.
sure.
Yeah, I think it's a really good question because I did mention that in my presentation around the need for us to work towards a standard, and the progress that has been made to this point is that we have a regular discussion, at least at the government level. So yeah, within my context in the Transport for New South Wales, as well as the Queensland made roads, we do discuss a lot of these issues at the national forum with the Commonwealth. And that's going to be a continual sort of a work in that space for us to hopefully align, and we don't have multiple standards across different jurisdictions, because that has been clearly been highlighted. And it's also part of the National Transport Technology Plan for us to work through these issues together.
And would you like to add anything to this, Dotun?
Yeah, I think that's really interesting. I think standardization is still not at the point where people would like it to be. There's still a lot of work that needs to be done for sure. In terms of how calves communicate with each other, there's I left that question to James because it sounds like there's a lot of trials going on around the V2X and V2V vehicle-to-vehicle type communications. And the interoperability is very important also, because how can you really safely deploy hundreds of vehicles on autonomous vehicles on the road? They need to be able to talk to each other, and they need to be able to work with each other to basically say, well, I'm stopping and you're going, etc. So that, and with platooning as well, there's a lot of space for development, and a lot of the stuff that we're doing is around closed, controlled environments. And the reason why we're doing that is because there's still a lot of room for improvement on how can the vehicles communicate with each other. So if we focus on one vehicle for now, then we can solve the problem later on with other vehicles.
Yep. So just because time is of essence, we might actually reach out to Christian and answer his question. So Christian, feel free to email us at monashcav@gmail.com. Other than that, thank you so much for everyone to attend tonight's webinar. I have definitely taken a lot of amazing points from both our speakers, and Rowan. Rowan's done all right. But yeah, thank you so much for coming, and hopefully you have a good week ahead.
Thank you very much.
Thanks very much.
Thank you.